All right, so as you can see here, I have a plot of two sine waves, and I actually have one of these marked as being a voltage waveform and the other one as a current waveform. So we have a voltage and a current. And so the first thing I'm going to do is just go through and write the time domain form for these, and then we'll talk about creating a phasor for them, and then we'll look at like I say, Ohm's law. So when we have our voltage waveform right here, and we can see that the peak value, V peak, is 2 volts. So remember in Blackboard, when we're putting things in Blackboard, we always need to do 3 significant digits. So there's 1 digit, 2 digits, 3 digits. Okay, and then there should be a space between the unit. Okay. All right, so we have the V peak is there. All right, so remember for a time domain representation, we have a voltage V, and this is supposed to be a T here. Okay, so what we're saying here is that the voltage V is changing with respect to time, and so it's going to have a peak value times sine omega t plus some phase angle. Okay, and so this is the general form of our time domain representation of a sine wave. And so remember, the V is lowercase, indicating that it's changing with time. And then omega is the natural frequency in radians per second, or the frequency that it's not really the natural frequency, but it's the frequency that the sine wave is running at. And then this theta here, okay, this is the Greek letter theta. Sometimes we use phi. Sometimes we use the letter phi, the Greek letter phi, for a phase shift or some other letter there. But the phase shift tells us whether it's crossing at 0. So you see right here is time t equal to 0. And so neither one of these sine waves are actually crossing at time t equal to 0. So you see that the voltage waveform is behind there. So there's a certain amount of time here it takes before the voltage waveform crosses 0 here. And so there's definitely going to be a phase shift. And as we're going along here, you know, if you have any questions, feel free to type them into the chat, or you know, if you have a mic, you can unmute your mic and ask your question. One thing though, if you're going to unmute and ask a question, I just want you to know that this is going to be posted. Okay, so I will be posting this video out on YouTube. And so if you don't want your voice on YouTube, then just put it in the chat window. Okay, and ask your question in the chat window. Or if you want, you know, put in the chat window that you want to ask a question, but I can kind of pause the video or something if you don't want it on there. Okay, but this will be going out on YouTube, so whatever you put in the chat won't be there, but what you know, if you speak, it will be recorded. So, all right. So, but anyhow, back to the sine wave then. We have the the waveform, again, is crossing after 0. So sometime after 0, the voltage waveform is actually crossing 0 and going positive. And so what we need to do here is find first the frequency. Okay, but we don't measure from 0 because the sine wave's not crossing at 0. So we have to measure first the period. How long is it taking to do one complete cycle, right? So you see this is one complete cycle of the voltage waveform here. Okay, and so you can see here that it's crossing at let's see, this is 0.45 milliseconds, okay, 0.45 milliseconds. It's crossing for the first time, and then it crosses again at 0.1711 milliseconds. And so the end time, so basically when we calculate the period, we need to look at the end time. Okay, so we're going to look at the end time minus the start time, which is over here. Okay, so the end time minus the start time. So that's going to be 0.01711 minus 0.00045. And so if we do that calculation, okay, I'm going to flip over to my calculator. You guys won't see it here, but I'm going to flip over just to make sure I 1711 okay, what did I, oh, okay, so just wanted to make sure I get it. So when I calculate that, then I get that to be so the period t is 0.01666, and then I'm actually, I only went out 4 digits there and 2 digits there, so I just have 4 significant digits here. However, remember, when we're going to put this into Blackboard, if I ask you to record what the period is, I'm going to put this into Blackboard. We would put this in as 1/6, so we have to move the decimal place over. So we have to move the decimal place over here 3. Here's my decimal point, so we're moving it over 3 places. And then, so that's 1/6, and then this 6 here, we need to look at the right and round up. So we're 5 or above, so we're going to round up. So it's 16.7 milliseconds. Okay. All right, remember your units. Seconds is time. You don't put a capital letter. So if we look at like units up here, we see that the voltage is V. Remember that was named after a scientist. So when we put it in as a V, it's capital V because it's named after a person. And the ampere, A is for ampere, and again, it's named over a person, so we need to capitalize those. But seconds is just time. It's not named after a person, at least not that we know of, because we've used seconds so long. So it's just time. But if we're writing them out, you see like over here when we're writing out milliamperes or volts, okay, when you write it out, you do not capitalize them. All right, so but this is what I would put in Blackboard for the period of the waveform. Now, before I get back to the voltage, I want to look at the period of the current waveform. So here's the period of the current waveform, all right? And it's, you know, here's one complete cycle of the current waveform. And so I'll flip over to red here for a minute, and I'm going to just kind of put that in there. So we have here that T is equal to the ending time. So here's my ending time, 0.1549 minus, right, because we're finding the difference here. But notice this one here, okay, this is a negative over here because it's crossing before time t equal to 0. All right, so this is crossing before the time t equal to 0. 1549 minus, and then that one is going to be a minus 0.00117 seconds. All right, and so if we punch that in the calculator just to make sure that because I want to know exactly what it comes out to be. So I'll punch this into my calculator. 0.1549 minus a minus. There's two minuses there, right? So it's a minus, so that makes it a plus. And okay, I was just wanting to make sure it because of the values displayed here, there may have been some roundup, but when I do that, I get the exact same 0.1666 seconds. All right, so again, we would put that in as 16.7 milliseconds. Okay, so now remember that voltage is what drives or pushes the current, right? The voltage is that potential difference that pushes those electrons to move. So when you calculate the frequency or the period for a voltage waveform and a current waveform, where the current waveform is being driven by the voltage waveform, these must be the same, okay? The period must be the same, and therefore your frequency is also the same, because you're being driven, it's being driven by the voltage. The current is being driven by the voltage, and therefore those two values must be the same. All right, so we have here the T, the time, or the PID, right? T, capital T is the period of the waveform. And so the frequency is equal to 1 over the period. So it's 1 over capital T. Now, when you do this, don't use your rounded up version of your value that you put into Blackboard. So the one in the box is what we put into Blackboard. But when we do the math, we need to make sure that we carry it out to more than 4 digits. I recommend when we have them out to 5 digits, so that the round off doesn't, otherwise you have round off error and it gets carried. So make sure you carry this out to you know, your 0.1666, and so you carry it out to more than 3 digits. I recommend 5 digits for most things. And if you do 5 digits, then when you round into Blackboard, you'll always be safe there. So when I do 1 over that in the calculator, okay, so when I do 1 over this value in the calculator, I actually get 60.024. All right, so the period is 60.024. But again, when we put this into Blackboard, then, so now when I put this into Blackboard, I would put in 60.0, and then the units for that are hertz, which is also known as cycles per second, but the proper unit is hertz. So this is how I would put it in Blackboard. But so you see this round off. Now, if I take 16.7, if I take the 16.7 milliseconds, I actually get, so if we use the value in the box, okay, so 1 over 16.7 milliseconds, if I use that value there, and I did 1 over that, then the answer I would get is actually 59.88. And so if I take that to 3 digits, then I would end up with 59.9 hertz, which, okay, the difference here is round off error, because rounded up, and then we use the rounded up value to do the calculation. Now we're getting an error. We're off by 0.1 hertz. Okay. And by the way, the electric company never lets the frequency get off by 0.1 hertz. That's a huge error for the electric company. The electric company monitors that frequency of 60 hertz, and they if it gets to 59.9 hertz, that's considered very, very bad for the electric company. They do not let that happen. Primarily because even that little bit will throw off their power factor, which we'll talk about later on. But they don't like that that frequency to change. Okay, they monitor the frequency, and it's supposed to be 60 hertz. All right, so that gives us the frequency, and I'm kind of running out of room here on the screen here, so let me write these over here, and then I'll clear off that side. So we calculated the period to be 0.01666 seconds. Right, which is 16.7 milliseconds, which is the value we're going to put into Blackboard. And then we have the frequency, then comes out to be 60.0 hertz. All right, so I'm just going to record those there so I can then come over here and clear this bit of screen here. So the next thing that we need to do is we need to find this angle. So we need to find this angle over here, this phase shift. Okay, so we know we have phase shift because the blue waveform is crossing after time t equals 0. So down here is time t equals 0. So this black line, I made it a thicker black line so we could clearly see where t is equal to 0 on the graph here. So we're crossing after, which means it's going to be a negative value for the phase shift. So the angle theta okay, which is our phase shift, is usually we like to give this in degrees. Well, actually, I'm sorry, I jumped ahead. We'll do the phase shift, but before we do the phase shift, let me just talk about omega. Omega is the radian frequency. Okay, the radian frequency is how fast, you know, you think about a generator. Okay, electricity is created by moving a magnet around and inducing a current in a coil. So as this rotates around, so as this magnet rotates around, whichever direction on the generator it's rotating, but this rotates around, we are, you know, the radian frequency tells you, like, at any particular time where that is at, as far as, you know, how many degrees of rotation, or, you know, what the rotation is. So radians are in rads per second. And so if we look at a circle, okay, remember that you have the radius of a circle. And a radian is like if you were to take this radius and start measuring the radius around the circle, and you go around all the way around the circle back to that same point, it turns out that you get 2 pi radians. Okay, so whatever the length of your radius is, you take 2 times pi times that radius, and that's the amount of distance you would travel to go around the circumference of that circle. Okay, so that's what a radian is. And so it's a physical measurement of where you are along the circle as it's rotating around. Now, degrees, we know that when you have a circle, if you have a complete circle, we know that a complete circle, if we rotate it around and we measure that in degrees, right, the distance around the circle is 360 degrees, or it's 2 pi radians. Okay, so the distance around the circle is 360 degrees, or 2 pi radians. Now, think about the sine wave. You've got this magnet inside here rotating around, all right, and it takes a certain amount of time for it to rotate around. The amount of time it takes for it to rotate around is that period. Okay, so one complete rotation is 360 degrees, 2 pi radians, or the period of the waveform. All three of these describe one complete rotation. Okay, so 360 degrees, 2 pi radians, or the time of the period that it took for one complete cycle. All three of these indicate one complete cycle. All right, so the radian frequency here, which we use as omega, this is the Greek letter omega. Looks kind of like a lowercase w, but it usually has a little extra curl in it. And this is equal to 2 pi times the frequency. Remember, we already calculated the frequency here. Or 2 pi divided by time. All right, and so if we take and we punch those numbers in, so we have 2 times pi times 60 hertz, okay, times 60 hertz here, and I'm just going to use the 60 because this is actually, you know, we calculated 60 hertz here, and there was a little bit of round off error due to our measurements from the graph, but it really should be 60 hertz. And so when we calculate this now, we end up getting out to 5 digits. I'll do it out to 5 digits first, but okay. So out to 5 digits, it's 376.99. 376.99, and the units for that again are radians per second. So what that says is it's running we're getting, as we rotate around, we're rotating around at 377 radians per second. So again, if we round this up to 3 digits, we would get 377, and then rads. A lot of times we write it as like rads per second. Technically, you could spell it out and make it radians per second, but rads per second is sufficient for Blackboard. Okay, so 377 radians per second. So I'm going to come over here. I'll just go ahead and record that. Okay, and you should probably put a decimal point there. It's just safer to put the decimal point. In this case, 377 is 3 digits, and there's no 0 there, so there's no confusion. So I'll take it either way. And you know, anytime if Blackboard like marks something incorrect, or you think it's incorrect anyhow, you know, feel free to send me an email. Make sure you give me the number, the question number, and the assignment there, and I will you know, I'll go in and look at it and make any corrections and give you points back. All right. Also, like if you just left out like a space or something like that between the number, the actual value, and the unit, or you left out your space, then you know, just let me know and I'll give you most of the credit there. I'll just like dock you 1 point for you know, for leaving out the space, because it's proper syntax to put the space. But all right, so now we've got our frequency omega, we've got our frequency in hertz, we've got our period. So now let's take a look at this offset. So we want to find out what this angle is. Okay, we know that it took 0.45 milliseconds, right, or 450 microseconds, if you want to look at that way, for it to before it crossed 0. So we're still working on the voltage here. So it took 450 microseconds, basically 450 microseconds after time t equals 0, before the voltage waveform finally started going positive, right? So the voltage waveform is 450 microseconds behind our reference. Okay, so this is our reference point. Okay, it's actually an arbitrary reference point, and I'll talk more about that when we get into I'm going to do a video for the oscilloscope here. But this is time t equals 0 is simply a reference point in time. Okay. Okay. And so that's our reference point, so that we can just calculate what our phase shift is. Now, so what we know, I wrote it up here, I got it in the box still, okay? So 1 complete period is 360 degrees. Now, normally for this phase, we put this in degrees because it's easier for us to look at a 15 degrees or 90 degrees and see that. If we put it in terms of radians, then it's some fractional number. All right, so it's actually easier for us to write the phase shift in degrees. We just have to be careful when we punch that into blackboard. So we have this degrees here, and we want to put it into degrees, and we know that 360 degrees is one complete cycle. So if we do 360 divided by time, right, both of these is one cycle. So we have one cycle, which is 360 degrees, and the period, right, in our case, the period is the 16.66 milliseconds. Okay, and that is also one cycle. So one cycle divided by one cycle, of course, is just simply 1. So we have here 360 degrees is one cycle, and 16.66 milliseconds is one cycle. So this is simply 1. So remember, if you multiply a value, say if you multiply 5 times 1, that's equal to 1, right? If you multiply 3.14159 times 1, you get 3.14159. So all we're going to do here is change units. We're simply changing units from time in milliseconds to degrees. All right, so we're multiplying by 1. So we're actually not changing the value, we're just changing the units. So we're going to take this time, okay, we're going to take this time here, which is 0.45 milliseconds, and we'll multiply it times our 360 degrees divided by our period, and I put it in milliseconds. Okay, it doesn't really matter as long as you're consistent, but now notice the milliseconds cancel, and I'm going to be left with degrees. So if we punch in these values then, so we're going to have 45.45 milliseconds times 360 degrees divided by 16.66 milliseconds. And that gives me 9.72 degrees. Okay. Now remember, this is after, it's crossing after time t equals 0. So this is going to be a negative sign. So our phase shift theta is going to be minus, because it's crossing after time t equals 0. And it's going to be minus 9.72 degrees. It actually came out to be 9.7239 degrees. And so to put it in Blackboard, I would put not minus 9.72. There's no round up here. And then degrees. So this is how I would enter this into Blackboard. Now, if you don't want to use the degree symbol in there, you could actually just put in a space and then spell out the word degrees. And it would be lowercase to spell that out. All right, so our voltage waveform now we can, all this, we can write our time domain form for the voltage. Okay, so our voltage waveform then, V of t, is equal to the peak value, which was 2 volts, so it'd be 2.00 volts, times sine of 377 t. Might want to put the period in there, but again, it's valid without the period because there's no 0. The units, okay, maybe use a different symbol here, times t plus, and then the phase shift Okay, I put a plus there for the phase shift, but looking over here, I see that it's actually should be a negative, right? So minus 9.72 degrees, minus 9.72 degrees, and this now is our time domain representation There's an I in there somewhere. It's kind of hard to see. But our time domain representation for the voltage waveform, which is the blue waveform. All right. So anybody have any questions at this point? All right. So I've done a couple of videos on this before, but I just want to walk through this again. You need to just be comfortable with this. You need to be comfortable with reading voltage waveforms off of a graph like this and being able to determine this information, because when we're in lab, we're going to be using an oscilloscope, and the oscilloscope is going to be showing us the voltage waveform as it moves here. And so we need to be comfortable with looking at a waveform and understanding what's happening. All right, so remember, we already looked at the period. We looked at the period for the current, and we saw that the current, the frequency and the period of the current waveform is identical because the voltage is driving the current. So the frequency omega okay, this here V, this capital V, if you're referring to that, okay, this is capitalized because it's a unit, volts. Okay, so it's capitalized because it's a unit volts there. Okay, so the lowercase v indicates that it is AC. That is correct. But if you're referring capital V right here, that capital V simply means that it's the unit voltage. Okay. All right. And when we put the voltage here, this is a variable. This is kind of a placeholder here. So I use a capital V here as the peak value, but it's not the DC value. It's the maximum value. And so we use a capital letter there to indicate that it's just a magnitude, but it's not the actual voltage, right? The actual voltage is defined by the entire equation. I don't know if that helps there. And when we get to phasors, use the DC equivalent, what we call the effective value or the RMS value, so those are actually also capitalized. So yeah, the book is correct. We use a capital letter for DC or the DC equivalent, and we use lowercase v to represent an AC moving voltage. Okay, but right here, this is just a peak value. This is just a peak value of the, so this one up here is just kind of a peak value representation there. So we usually use that as a capital V because it's a peak. Okay. But the entire voltage, when we're just talking about the entire voltage, that in AC that would be lowercase. And now we want to create the time domain for the current. And so as I was stating, right, it's the exact same frequency. So the frequency doesn't change. And the magnitude here, we see that the current is 1, but this is given in milliamperes, okay? So, or the peak value of the current is 1, but it's in milliamperes, so it's 1 milliampere. And so all we really have to do now to go to the current, I mean, we find the peak value, but to find the current, now we have to just look. We know the period is the same, but we have to find the phase angle, because in AC circuits, the phase angle is quite often different for the current than it is for the voltage. And so what happens is, and I mentioned this last week, we have something we call Eli the Iceman. It's just a reference point. I don't know who came up with this, but oops, ice. Okay, so we have Eli the Iceman, and what this says is that in a capacitor, the current leads. In a capacitor, the current leads the voltage. And in an inductive circuit, the voltage leads the current. And so what we see here in this case is that the current is crossing before, the current is going positive before the voltage does, right? So you see here that the current is crossing 0 before the voltage does. It actually, in this case, it's actually crossing also before time t equal to 0, but that has nothing to do with Eli the Iceman. The important thing is that the current is crossing 0 before the voltage crosses 0. That is all about Eli the Iceman. It has nothing to do with the reference time frame here. So we know just by doing that we know that we have capacitance in this circuit. Okay, that is a given because the current waveform is going positive before the voltage waveform goes positive. Okay, so the current is in front of the voltage. So that is Eli the Iceman. So we know in this case that I have capacitance. Now I probably also have resistance in this. Actually, I know I do. You can actually see it right here because it's not a 90-degree angle. But we'll get into that a little bit later, but I know that we definitely have some resistance also in this circuit. But just very, very quickly, I can look here and see that we have the current is ahead of the voltage, so I have capacitance in my circuit. I may have some inductance also in the circuit, but I know that I have more capacitance than I do inductance. All right, so, and we already said the frequency doesn't change, but what we have to do is to find out what is this phase shift. Okay, what is the phase shift? And the phase shift we're looking at is the phase shift between time t equals 0 and this crossing 0. Okay, and so we calculate that same way we did it before. Remember, 360 degrees is equal to 1 period. So we look at this, and this is the time here. So it's a negative value because it's before time t equals 0. So it's minus 0, 0, 117 times, and that's seconds, okay, so I wrote that in seconds, times 360 degrees divided by the time in seconds, which is 0.01666. Now remember, use your more accurate version, don't use the rounded version. And so I'll punch this in the calculator to see what I get. So 360 divided by, and so I get 25.282. So this is the phase angle for the current. So maybe I'll put a little subscript here for the current. And so that's 25.282. Now remember, the units here was given in seconds, so the seconds cancel, and I'm left with degrees. And so this is 25.28. Okay, so that's going to round up to be 0.23 degrees. So when I put it into Blackboard, it's 25.3 degrees. So if we wanted to write our current waveform now, we'll get I of t. Okay, so again, this is lowercase because this is AC. And we will have to put the peak value. So the peak value here was 1 volt, so it'd be 1.00 volts. Now remember, this is the unit volt, so that's why this is capitalized, times sine. And then we have our 377 T rads per second times T. And then this is a plus sign. Okay, so see, this was negative, but this here had a negative there. So it actually get a double negative, or just the fact that because it's in going positive before t equals 0. Okay, so it's ahead. So the positive means that we are ahead. And our value then of that would be 25.3 degrees. So this is our current waveform. We have our voltage waveform, and we have our current waveform in the time domain representation. All right. So I think the big things here are calculating these angles. So remember, to calculate the phase shift for that angle of the phase shift, you know that one period, capital T, is equal to 360 degrees, which is also equal to 2 pi radians. It's the complete rotation, one complete rotation of our magnet inside of our generator that's generating that. And so it's one complete rotation, and so that is where this conversion goes. Another way of looking at it is the fact that one complete cycle takes 16.66 milliseconds, or 0.01666 seconds, and we're we're ahead by this amount of time. So you could look at it more of as a percentage also. But you need to be comfortable with calculating these phase shifts. Okay, so now notice there's an angle. The angle between the voltage and the current okay, this angle is your 25.3 degrees. And the difference, we're looking at the difference, so that actually should be a negative sign up here. This should be a negative because we're looking at the difference. All right, so it'd be a minus 9.72 degrees. Okay, so the difference between these then is actually going to be a positive, right? Because we got dual negatives there, so that actually becomes a positive. And so it's actually then going to be 35 degrees. Okay, so the phase angle between the voltage and the current. So the phase angle is actually going to be 35 degrees between the voltage and the current here. 35 degrees. All right, so the next thing that I want to discuss then is phasor representation. So if we have a sine wave, so I'll just kind of sketch I'm just going to try to sketch a sine wave here just very roughly. All right. And so when we look at this sine wave, you see that it's got a positive value and it's got a negative value. So it's positive for half the time and it's negative for half the time. So if we looked at the average voltage, if we looked at the average of this waveform, V of t, the average is equal to 0. So the average voltage is equal to 0 volts. And we know from DC circuits, at least, that power is equal to volts times the current in DC. And so if we were to take the average voltage of our AC waveform and kind of plug that in for the voltage, then that would indicate that we have a power of 0 watts, whatever the current is, right? If the average, so this would give us an average power of 0 watts. But we know for a fact that AC does provide power. And so we average power, looking at the average for AC circuits. If you tried to use like the average over a period and you looked at the average of the voltage, you would get 0. If you looked at the average of the current, that would be 0 also. So we can't use the average value. And I did talk about this last week, but I want to just go through it again because it's very, very important. And so I just kind of want to reinforce this. So what we do then is we want to take and create an effective voltage. So if we have our waveform here, okay, and we try to take the average to determine the average power, that doesn't work. So what we're going to do is we're going to square it. So we're going to square our voltage. And so when we square it, right, it's going to be squared. So this part here ends up being, you know, the square of that. But then the negative part, because we've squared it, it becomes positive also. Then we're going to take the average. So now we can take the average and not get a negative. Okay, so the other word for average is the mean value. So mean or average both mean the average of this. So what we're going to do, we've squared this. So it looks like this, but now we're going to take the average. So what we're going to do is these peaks, we're going to take the peaks here above this average value and fill in these gaps in here. Okay, so by taking the average, we're leveling this off. Okay, I think there was an analogy in the book or on the one video I gave you talking about a pile of sand, and you're just leveling it off so that you get this nice average value, so it looks almost like DC. Now this is over one period of your waveform, and you just do this, you know, you do for one period as long as it's consistent. Long as the waveform is unchanging, it'll be work. But now we've got the average of the square. So now what we have to do is we have to take the square root. Okay, so we take the square root of this, and so we have root mean square, and this gives us the RMS. Okay, root mean square gives us the RMS value. So RMS comes from the fact that we've squared it, we've averaged it, and then we took the square root to get back to that value. And the RMS turns out to be equivalent to the DC. So if we just had a constant DC, remember DC means it's constant, unchanging, always going in the same direction. AC means it's alternating, which means it's going in one direction half the time, and then it's flipping around and coming back in the other direction. And so the DC, all right, we worked with DC all last semester or whenever you had the class, but you know, and we know that we get that power. You know, power comes from V times I for DC. Okay, and so that gives us our power. And the you know, so the RMS value is in fact equivalent to the DC. So the book also refers to this as the effective. Okay, so the effective value is the RMS value. Now, I'm not going to do the math for you. The book does walk through the math, but what turns out, this is kind of an amazing thing to me, but it turns out that when you do this for a sine wave, okay, the RMS value, so we use a capital letter for the RMS value because it's equivalent to the DC. So this goes back to the question you had earlier. And so the effective value, DC, we use DC for, we use capital letters for DC, so we are also going to use capital letters for the RMS value because the RMS value is equivalent to the DC value. And VRMS is equal to the square root of 2 if it's a sine wave. I need to make sure that you understand this. If it's a sine wave, then the RMS value is the square root of 2 times the peak value. Okay, so the RMS, or the DC equivalent, or the root mean square value of a sine wave, is equal to the square root of 2 times the peak value. Okay, and this only works for a sine wave. And one of the things that just blows my mind about this is the square root of 2 is an irrational number. So remember, like, we were already using pi to calculate radians, okay, which is an irrational number. And square root of 2 is also an irrational number, okay? So it turns out, you know, square root of 2 is like 1.414, okay? And so, but it's an irrational number like pi, that it doesn't, you know, stop as you take it out to more and more digits. It doesn't actually stop, okay? But the right here, this is very important. Maybe I'll stick it up here somewhere. All right, so this RMS value is equal to the square root of 2 times the peak value of the sine wave. All right, let me just kind of clear this off here again. So then we can talk about converting between phasors. All right, the other thing I want to remind you here too is we talked about, we calculated the phase angle. We talked about the phase angle between the voltage and the current, and that turned out to be this 35 degrees here. Okay, so keep in mind of that. All right, so now we're going to go to the phasor domain. Okay, so we're going to go to the phasor domain. Kind of write it in bold here. Okay, so the phasor domain all right, so if we have a time domain representation, okay, the phasor domain, number one, you write the voltages. Or you write, you write the voltage or current magnitudes. Using their RMS or DC effective value. Okay, so when you're going to phasor domain, we're going to use that RMS, which is the DC effective value. And when you're going to the phasor domain, okay, the thing with the phasor domain, we're going to, does not show so it does not show the frequency of the waveform. All right. So see, with the time domain here, with the time domain, we have the frequency of the waveform. We write it in terms of the angular frequency, but we know what the frequency of the waveform is. The phasor domain is a representation of the same waveforms, but we don't actually show that frequency. That frequency is embedded inside of the phasor domain representation, but it is not visible. You can't look at a phasor representation of the waveform and see what the frequency is. It's just, we don't have that information in this, so we just, obviously we know it's an AC waveform, so therefore it has a frequency, but simply looking at a phasor representation of it, we do not know what that frequency is. All right. And the third thing to note then is that we do show the angle. Okay, we do need to show the phase angle. Okay. So when we're doing the phasor domain, we have 3 points here. Number one, we want to write the voltages in terms of their RMS, which is their DC effective value. We're going to pretty much ignore the frequency, okay? And then we are going to, but we do keep the phase angle, okay? Because it's a phasor. That's kind of a hint that we need to keep the phase angle, and we need to keep the magnitude of the voltage, but we're going to ignore the frequency. Okay. That doesn't. All right. Now, so when we do this, then we need to write it in the DC effective value. And so when we write it, number one, going back to the question that we had earlier, we're going to use a capital V to indicate the phasor domain and V for voltage. And a lot of times I'll put a line either above it or under it. Okay, so the phasor, we put a line, we like to put lines above it, but sometimes it's easier when I'm typing it out inside of a word processor or inside a Blackboard. It's much easier to put an underline under there, right? Because you can just do like a Control U in your word processor tools, and that'll give you an underline. But this here line indicates that there's going to be a phase angle. So we use a capital letter and we use a line in there to indicate that it's a phasor. All right, so this is a voltage phasor, and we're going to write the voltage in terms of the RMS value. All right, well, I have over here that VRMS is equal to the square root of 2 times the peak value. Well, I have the peak value. Here's my peak value. And so the I'm sorry, I wrote that. Nobody caught me on that. I wrote that backwards. Let me go back to the sine wave here for a minute. Okay. If this is my sine wave, and this is the peak value here, then the RMS value needs to be less than that. Okay, so I'm sorry, I apologize for this. I wrote this wrong over here. Can't believe I've done half the video on this, and this is incorrect now. I just have it. The RMS value must be less than the peak value. So when I wrote this up here, when I wrote this up here, it should be V peak. It should be V peak divided by the square root of 2. Okay. Sorry about that mistake there. It's really easy when you think about this drawing here, right? The RMS value is less than the peak value. It's got to be less than the peak value. So the RMS value is equal to the peak value divided by the square root of 2. And if you write it the other way, the peak value is the square root of 2 times VRMS. That's what I had written, but I had my peak and my RMS backwards. Okay, so I apologize that. So the RMS value is smaller than the peak value. Hopefully that makes sense. And I apologize for writing that incorrectly there. Okay. You know, if you guys catch me, you know, doing that incorrectly there, just, you know, please put something in the chat or whatever and question me on that. But I apologize for flipping those like that. But like I say, if you think about this sine wave here, so if you think about this little waveform right here, the way I've drawn it, the RMS value must be less than the peak value. Because the fact that it's negative, well, not the fact that it's negative, but the fact that it's less than the peak value most of the time, right? It's only the peak value for basically one instant of time. And so therefore, the effective value can't be more than the peak value. That just doesn't even make sense. So I always use that as a guideline, but I just didn't stop and double check that as I wrote it. But the RMS value must be less than the peak value because you're only at the peak value for just a brief amount of time. All right. So right here, you're just at this peak value for a very brief amount of time. So the RMS value must be less than, so you do the divide. So to go from peak to RMS, you're dividing because it needs to be smaller than that. To go from RMS to peak, that's when you multiply. So let me clear these up here for a minute. It's running slow again. All right, so then back to the phasor. So now that I've got the equation written correctly here, so remember, we're going from that peak value we have the peak value. The RMS is always going, well, it's not a very straight line, but the RMS is less than the peak value, so we're going to divide by the square root of 2. So we have here 2, our peak value was 2. Okay, so the peak value was 2 volts, and we're going to divide by the square root of 2. All right, and so that is going to give us our 1.414. So our voltage now is 1.414 volts, and then we're going to write an angle. Then we have to have the angle, and the angle is really easy. You just copy the angle, minus 9.72 degrees. So here is our phasor representation of our time domain sine waveform. So again, this is the RMS value. If you want, you can actually write RMS in lowercase down here. Technically, RMS is an acronym. Root means square. And so, you know, you could think, well, maybe it should be capitalized because it is an acronym. But you know, common usage, we write it in lowercase because we're already writing the capital V for voltage. Remember, this V here is capitalized because it's simply the unit voltage. And so we write like V and then RMS. We usually write this lowercase, even though it is for an acronym. All right, but this is our phasor domain representation of the voltage. Okay. And then we can do the same for the current. So our current waveform, again, capital because it's the effective DC effective value. So we capitalize it and then we either underline it or put a line above because it's going to have a phase angle. And so we're going to take 1 volt, 1 ampere or 1 milliampere. I'm sorry. Doggone it. This should have been milliamps up here because this was a current. Okay. Okay. This was a current here. So that should be milliamperes, not volts, okay, because that was I. So, but anyhow, so we're going to take 1 milliampere, divide that by the square root of 2, and what we're going to find is that gives us 0.707, okay? 0.7071 if you take it out to 4 places. So 0.7071 milliamperes. Now to put it in Blackboard, we're only going to do 3 significant digits. But when you're doing your calculations, carry it, so make sure you record those extra digits. Same thing for the voltage, right? When we put it into Blackboard, it would just be 1.41 when we put it into Blackboard. Okay, and don't worry about putting the RMS into Blackboard, just capital V for volts or space MA for milliamperes or whatever the case may be. But the phasor is, for the current, is 1 milliampere divided by the square root of 2, which gives us 0.7071 milliampere. Okay, and then we have an angle. And the angle is positive 25.3 degrees. So that is our angle. Okay, so again, when we put them into Blackboard, you need to make sure that you just do the 3 digits. So we would put in like 1.41. But when you're recording your values to do other calculations, you want to take it out to 4 or 5 digits, significant digits, so that you don't get round off error for your additional calculations. All right, is there any questions? Stop at this point and just see if there's any questions there. I know there's a lot of material. The good thing about doing these lectures this way is that, you know, this is being recorded, and as I said before, I will post this into YouTube and put the link into Blackboard so that you can review this later on. And you can go back through there. So, but all right, so if there's no questions at this point, I want to talk about Ohm's law next. Okay. Let's see. I need to just try and clean some of this out of here a little bit so I have some more room to write. So we have our voltages, or voltage, and our current here. All right, so we know from DC circuits we know that Ohm's law is the voltage divided by the current. Ohm's law says, like, the resistance in DC, this is for DC circuits, the resistance is the voltage divided by the current. But now we are in AC, all right? And so for AC circuits, all right, we have a new term here. We have, over here, we have resistance, okay? And resistance doesn't change. But we have a new letter we're going to use, Z, for impedance. Okay. And impedance is the opposition to current flow in an AC circuit. Okay, so resistance, remember that resistance is the opposition to current flow in a DC circuit. Okay, so resistance opposes current flow, right? That's what resistance does. Well, in an AC circuit, if you have a resistor in an AC circuit, guess what? It's going to oppose current flow. So resistors don't care whether you feed them AC or DC, they are going to oppose current flow. And so that doesn't change. However, in an AC circuit, you also have capacitors and capacitors and resistors. So in an AC circuit, we're going to have resistors, okay, so we are going to have resistors or resistance in an AC circuit. And so that, of course, is resistance. And if you remember, we talked a lot about this in DC circuits. Basically, what resistance does is it takes and it converts electrical energy into what? Somebody type that answer in the chat window. A resistor converts electrical energy into thermal energy. Absolutely, that's correct. So it converts it into thermal energy. Thank you for participating here. So it turns it into heat. Okay. Okay, converts electrical energy into heat. I'll just kind of draw an arrow here or something. So it converts it into heat. However, now we're going to we have capacitors, okay? And we have inductors. Now, and capacitors and inductors react to the flow of current. Okay, so we have something called reactance. Okay, and reactance is the opposition to current flow due to capacitors or inductors. And reactance, we use the symbol X for reactance. And so a lot of times we'll put X of C for capacitive reactance. And capacitive reactance opposes current flow, but it doesn't cause heat. What we do with a capacitor, if you remember from the last part of DC circuits, capacitors store charge in an electric field. So the reactance is the act of storing the energy. Capacitive reactance stores energy into the electric field of the capacitor. Because remember, capacitors, we simply charge those things up. So we didn't lose energy, but we converted that energy. We converted that moving energy, that kinetic energy. If you have had physics class, they talk about kinetic energy. Kinetic energy means that it's basically moving. So electricity is moving electrons, right? So that is moving energy. And we're going to take that and store that energy into a static energy. And we're going to store that in the into that electric field of the capacitor. And so when we store that, right, that act of converting that moving electricity into a stored energy opposes current flow. All right, so there's an opposition to current flow because of that transfer of moving energy into stored energy. And therefore, we get this opposition to current flow, and we call that capacitive reactance. Now, with an inductor, I'm going to resize a little bit here to give me a little bit more room. Okay, an inductor, on the other hand, stores energy into a magnetic field. Okay, so we have something we call inductive reactance, and inductive reactance stores energy into a magnetic field. Okay, so resistors convert the energy into heat. Okay, so resistors convert electrical energy into heat or thermal energy. Once you do this, once you put that electrical energy through the resistor and convert it into thermal, right, then that is radiated out as heat, and that energy is gone. I mean, it's, you have heat now, but you don't have any electrical energy. Capacitors take that kinetic energy, the movement of the electrons, that electrical energy, and they store it into an electric field. And then, but that's like during the first half of an AC cycle. So remember, with a AC, we're going positive half the time, and we're going negative the other half of the time. So what happens is during the positive cycle, you're charging up the capacitor and you're putting a positive field, or you're putting electrons on the bottom and taking away electrons from the top, and you're storing that energy inside of the dielectric, inside of that magnetic field. Okay, but that's only during the top half. Now, when the sine wave goes negative, you're going to reverse. So you're going to take the energy and you're going to flip the energy and you're going to store it in the opposite direction. All right, so you're constantly building up this electric field and then taking down the electric field and putting it on the other side in the opposite direction. So you're getting like plus minus, and then minus plus, and then plus minus. So you're constantly, as the sine wave, as you have these sine waves going on and on and on and on here, okay, those turned into triangular waves here or something. But as they're going on and on and on, you're constantly storing energy into that capacitor or into the magnetic field of an inductor if you have an inductor, and then during half of the cycle, and then the other half of the cycle, you're going to take it back out and shove it in the other way. And that's opposing the flow of electricity, but it's not using the electricity. And so we call that reactance. So the act of storing the energy into either an electric field inside of a capacitor or the magnetic field inside of the inductor is called reactance. And so we use reactance, okay, as a measurement. Now the units of reactance, because it's still the opposition to current, okay? Resistance is the opposition to current, and reactance is the opposition of a current. And so they, no matter which one you have, the units is ohms, right? Ohms is the resistant. Ohms is the opposition. I should use the word opposition now. Ohms is the opposition to current flow. It's the unit of measure of the opposition of current flow. So just like it was in DC, ohms is the opposition to current flow. It's the unit of measurement for the opposition of current flow. But we have this reactance. Okay, reactance is used the symbol X, and again, X with a subscript C for capacitive reactance, and X with a subscript L for inductive reactance. So we have this impedance Z. Okay, so the impedance Z now is a vector. It has, or a phasor. It has an angle associated with it. So the impedance to current flow is the combination of the resistance and the reactance. Okay, so Z, the impedance Z, is equal to the resistance still waiting on the software to catch up to me here. So the resistance plus J, I'll get back to J here in a minute, plus the inductive reactance minus the capacitive reactance. Okay. All right, good question there. Why do we want to use capacitors, and why do we want to use inductors? And there's several different reasons for that. We'll get into those later on in the semester. One thing that they do is that we use them to filter the the electricity. So we use capacitors and inductors as filters. Okay. So again, the question is why? What's the benefit of having a capacitor and an inductor in the AC circuit? Well, we can use those to create filters, and like I say, we'll talk about those. I forget which chapter, but later in the semester we'll talk about filters, and they allow us to filter out certain frequencies or all frequencies to make DC from an AC circuit. Okay, so we use them to filter it out. But another thing is, like when we build a motor, okay, an electric motor is built from coils of wire. And so when we build a motor, what we're doing with a motor, so an electric motor is built almost like the generator we were talking about. So we have a coil of wire, and we have a magnet, okay? And if we pass a current, through, so if we feed a current into this coil of wire, we can make the magnet rotate, okay? So by feeding the current into the coil of wire, we cause rotation. So an electric motor takes that electrical energy and turns it into mechanical energy, specifically rotational energy. But a motor converts electrical energy into mechanical energy. But notice that we did this with a coil of wire. And what's a coil of wire? An inductor. All right. So we build motors to take this electrical energy and convert it into rotational mechanical energy. But because we built the motor using coils of wire, we put inductors into the circuit. And so, you know, all electrical motors have inductance in them because they're coils of wire. They're made with coils of wire, so therefore they have inductors in there. So, you know, we didn't really build the inductor to have an inductor in that case. We built the inductor to get the mechanical energy. But by the fact that we built that motor using coils of wire, it gives us inductance in the circuit. So all electrical motors will have inductance in there. All right. We don't really want the inductance. I'll maybe talk about that a little bit later. But it's there because what we want from an electrical motor is the mechanical energy. But we build the motor using coils of wire, so we have inductance in there. And so we just have to live with it, basically. But hopefully that kind of answers your question there about why we would have inductors or capacitors in there. Like I say, some of that will probably become even clearer when we start talking about filters and power factor correction and that kind of stuff. But this reactance, why we put capacitors and inductors in there, because we're trying to perform certain things, like to build an electric motor. To build a electric motor, we have to use coils of wire, so that automatically gives us inductive reactance into the circuit. Okay. All right, so but this opposition to current flow, again, we call this impedance. Okay, so the opposition to current flow is impedance, and we use the symbol Z for that. Okay, so it seems like I got off track. I wanted to talk about Ohm's law, but I had to introduce impedance here. So now for an AC circuit, Ohm's law still applies, okay, but now Ohm's law, instead of simply using R, we have Z, the impedance, okay, which remember it has a phase angle to it, Z, and that is equal to the voltage divided by the current. Okay, so Ohm's law didn't exactly change on us. Ohm's law is still the voltage divided by the current gives us the opposition to current flow. What changed is the fact that we have a phase angle. Okay, so if I wanted to calculate the impedance, here's my impedance, okay, and this impedance is the voltage, okay, which is 1.414. And again, this is why we want to carry it out when we're to multiple digits here instead of stopping at 3 digits. 1.414 volts RMS divided by 0.7071 milliamperes. Okay, but then remember there's angles associated with these. So we have an angle of minus 9.72 degrees. And an angle of plus 25.3 degrees. And so if we calculate this now, we're actually going to get 2.00 at an angle of minus, now I calculated the angle up here, but I didn't actually specify whether it was positive or negative. It turns out that it's this angle, right, this is minus 9.72 here. This is positive, but it's in the denominator, so it turns out to be minus 35 degrees. All right, and I forgot my unit there. Remember, I already stated that the units of impedance are in ohms, just like in DC circuits. All right, so using Ohm's law here, I calculated the impedance is the voltage divided by the current. And so we get that the impedance to current flow is, given Ohm's law, voltage divided by current. The difference now that we have to keep track of the angle. Okay, so we have to keep track of the angle. All right, so now notice this phase angle here. So I mentioned earlier, way back at the beginning of this, I mentioned that this circuit had a capacitor in there. I knew that the circuit had a capacitor in there. Well, if you look at the form of impedance, this is what we call the rectangular form. This is the rectangular form of impedance. And this one over here is called the polar form of impedance. Okay, and so you know the book walks you through lots of different ways of converting back and forth there, basically what you need to do is think of this as a triangle. And on Wednesday, I'll go over phasor diagrams and stuff in detail. But we know that we have resistance, and we know that we have reactance. And this reactance is actually negative because it's a negative angle over here. All right, so I have resistance, and I have capacitive reactance, and so the impedance is the hypotenuse of this triangle, and the angle is minus 35 degrees. So therefore, I can calculate R. R is the adjacent, right? So R is equal to Z times the cosine of our phase angle. And X of C is Z times the sine of our angle. Okay, and so we can calculate the value of resistance. How much resistance is in this circuit? Now notice, all day long, I have yet to actually draw an electrical circuit. All I started off with back here, right, was with a voltage waveform and a current waveform. So I haven't even drawn an electrical circuit. So let me draw an electrical circuit right now. So here's an electrical circuit with a voltage, and I know that I have a resistor in this circuit, and I know that I have a capacitor in this circuit. Okay, and so there's my electrical circuit. Okay, and I can calculate what the value of resistance is, and that just comes from Pythagorean's theorem, right? So this is why you have to take trigonometry for this class, right? Because you have the resistance and you have the reactance, and this is a right triangle here, okay? And so you have minus 35 degrees is the overall angle, and using trigonometry, we can calculate the resistance. And we can calculate the reactance. Now, we can do each one individually, but if I'm going to do this in a calculator or in the Octave software, so you guys know I like to use the Octave software. Let me flip over to the Octave software, and I'll show you how we calculate this using Octave. I know quite a few of you started using Octave the other day, or the last semester, I mean. All right, so here is my Octave window. Hopefully it's going to move over. Hello? All right, this computer here, I actually have 3 monitors on this computer, and it therefore I think it messes up sometimes when I start trying to switch screens. I think it has something to do with that, and it just kind of hangs my display on me sometimes. So I had to come back in, which means I lost because I did not save that image before, so I lost everything. So I'm going to write these down here. So let me just kind of write here the waveform, if I remember. You guys correct me if I'm wrong, because I'm going from memory here, but I believe that my phasor VRMS, all right, that was, I'm just going to write this in a string form for the moment. I believe that was 1.414 volts at an angle. I'll just use a less than to kind of indicate an angle. Again, I've got a comment here. I got a quote here, so this is just going to be string form. I'm putting it in right now. But the angle, anybody remember the angle? Sorry about that. I think I did have that saved. .72. Yeah, that's what I was thinking. Thank you. But 9.72 degrees. All right, and then IRMS was 0. 7071 milliamperes. Oh, and that, this angle is plus. What was it? 25 point something, 25.3, something like that. Yeah, degrees. Okay, so VRMS, this was a negative. Okay. All right, so now if I'm going to put these into, let's see, so the impedance then, Z, okay, my impedance, we calculated that to be 2.00 at an angle of 35 degrees. Okay, so Z, and Z isn't an RMS value because it's not a sine wave. Okay, Z is an impedance. Okay. So Z is an impedance. It's not a sine wave. It's not moving. Okay, it's just an impedance, and so therefore it's not really an RMS value. So you don't put like Z RMS. But Z, if we put it in polar form, okay, we have to put it in there. Now, if you have a TI-84 calculator, or you're using Octave, which I am, okay, if you're doing either one of these, ignore those errors. I'm just trying to type in this window so that you can see what I'm saying. But when you do this, you need to put it in radians. The angles must be entered in radians. Okay. If you have, again, if you have a TI-84 calculator or you're using Octave, you have to be careful. You have to put angles in radians. But the angle that we had for our impedance, okay, Z, and I'm going to put this, this is just a string, okay. Z was 2.00 ohms at an angle of minus 35 degrees. Okay, and so if I'm going to put this into my TI-84 calculator, if you want to do it there, or you want to do it in octave, you have to put it in radians. And so the way we do this is I'm just going to say like Z is equal to, okay, so Z is equal to 2.00 times E, and actually an octave in your 84 calculator, right, you find the little E. This is Euler's number. You find that little E to the X thing in there, that symbol on your calculator, wherever it is on your calculator key. But in octave, you actually type it EXP. And now I'm going to put it in, we have to put J. Now, J, I mentioned J before. J is equal to the square root of -1. Now, J is already in octave. And the letter I is also in octave. They're both the square root of -1. So J is equal to I, which is equal to the square root of -1. Now, mathematicians like to use I for the square root of -1. But the problem that we have for doing electrical, we already use I for current, right? We use I as the symbol for current. So we don't want to use I for the square root of -1, and that's why I was using J. So we're going to use J for the square root of -1. Now, when you, so when I type this in, I'm going to type in Z is equal to the magnitude, which is 2 ohms. But we're not, you can't put units in your calculator, times Euler's number minus, because minus 35 degrees, so minus J times 35. But this is degrees, and I just said before we need to put it in radians. So remember that 2 pi divided by 360, that's our conversion factor. Okay, so you can do 2 pi divided by 360, but if we divide the top by 2 and the bottom by 2, you get pi divided by 180. So it's a little easier to type that. Okay, so we have 35 times pi divided by 180. This makes it radians. This converts it into radians. And again, if you have a TI-84, this is how you have to put it in. If you have a TI-89 calculator, okay, so if you have a TI-89, you could actually just type in something like this inside your TI-89. You could type in like 2, and then use there's an angle symbol on your TI-89 calculator. And then you could just put in the angle minus 35. If you're in degree mode, you can punch it in your TI-89 calculator like this. Okay, but a TI-84, you have to do this conversion and put it in radians. It doesn't matter whether your calculator is in degree mode or radian mode. When you're trying to type this notation into a TI-84 calculator, it must be radians. All right. So anyhow, when I type this in here, you see that I get the result in rectangular form. Okay, so this gives me that result in rectangular form here. And so remember that Z is equal to R plus J times a positive X of L minus X of C. And since this is negative, as I said before, that is negative, then there is no X of L. Or at least if there is, what we're getting is there's less capacitive than there is inductance. And so what we're doing is just getting the X of C. So what this tells me is that the amount of resistance in my circuit is minus 1.638 ohms. And the amount of capacitive reactance is 1.1472 ohms. Okay. So this is the amount of resistance in that circuit. And this is the amount of reactance. The total effective amount of reactance in that circuit is capacitive. Because it's a negative number, I know it's capacitive. Or because the current is ahead of the voltage, Eli the Iceman, I know it's capacitance. And so therefore I have this minus X of C in my answer. So this is the impedance. This is the polar form of the impedance. This is the rectangular form of the impedance. Okay. Again, I will continue on with this. We're pretty much out of time here, but I will continue on with this next week, or no, excuse me, let me return on Wednesday, not next week. Next, on Wednesday, I will continue on with this, and we will have, I'll do a bunch of examples, and I'll do something called phasor diagram. So I'll show you how you can draw this mathematically. We can using Pythagorean's theorem, right triangles, we can actually draw the voltages or the currents, and we can calculate the voltages and the currents. We can verify Kirchhoff's voltage law using triangles. We can verify Kirchhoff's current law using triangles. All right, because we have to use triangles because of these phase angles, right? We got 35 degrees here. Okay, but we can verify like Kirchhoff's voltage law, but because we have phase angles, we have to be careful and we have to track the angles. And so therefore we can't just simply add them, we have to add them including the angles, but we can do that using triangles. And so I'll be doing some examples of those on some videos and uploading those. All right, so like I say, we're pretty much out of time here today, but hopefully this question, is it possible in an AC circuit sine wave to start with 5 volts on the positive wave and on the bottom to be 10 volts or 3 volts? Okay, good question. What that means, yes, what that means is that, let me see, I'm going to flip back over to, hopefully it doesn't lock up on me this time. I'm going to flip back over to my image. Hey, that didn't lock up on me that time. Sometimes it does, sometimes it doesn't. All right, so a sine wave is pretty much defined as starting at 0, going to the positive peak value, going back to 0, and going to the negative peak value. So you said it like it'd be 5 volts, so we'd have like positive 5 volts up here and minus 5 volts down here. Now, if you have a DC, so if you have a DC voltage and then the sine wave is riding on top of the DC voltage. So let's say that we had 8 volts DC. So 8 volts DC, and this was a 5 volt waveform. So the peak value now when the sine wave is at peak and it's 5 volts, you have 8 plus 5, so you would have, it would be peaking out at 13 volts, and then the minimum here would be positive 3 volts. Okay, so what happens there is you have a DC voltage and an AC voltage, so the DC voltage is basically riding on top of that. So if we wanted to write that, we would actually write the voltage waveform as being a constant DC. Okay, so it would be 8 volts constant DC plus, I don't really have room here, but plus the sine wave of 5 volts times sine, whatever the frequency was, sine 377t or whatever the frequency would be. So we have DC plus AC running together. And in fact, that happens all the time. That's happening in your computer right now. You have a DC waveform riding on top of your AC waveform. Or I mean your AC waveform riding on top of your DC waveform.